Good morning. I'm Sean Tyson, the U.S. co-chair for the Reliable Nuclear Fuel Services Working Group. I'd like to welcome you to the second day of our webinar on understanding deep borehole technology in the context of spent fuel and high-level radioactive waste disposal. Thank you for joining us this second day. I'm very much looking forward to a continuation of our discussion and most especially the discussion at the end of the presentations. So with no further ado, please, let's begin the program.
So short good morning, good afternoon, good evening from my side. My name is Tomasz Żagar, the other co-chair of the working group. And I'm also looking forward to see this more practical, hands-down day of the webinar. I'm sorry I have to leave sharp at the end, so I will ask Sean to close and say goodbye and thank you also in my name. And now, please, Neil.
Yes, and good day, everybody. My name is Neil Chapman. I'm going to be moderating the session again today. For those of you who weren't with us yesterday, I'm a geologist with many, many years experience in deep geological disposal. I'm working currently on a whole range of areas, including multinational solutions as one of the topics I'm particularly interested in. In a little while, I'll ask our panel members for today to introduce themselves. The plan for today is that we will have a closing panel session that will be joined by the panelists who you will have seen speaking yesterday. And because we have less presentations today than we had yesterday, we're expecting to have more time for discussion and to get down to some of the questions that we looked at yesterday. Just a reminder, if we could put up the first slide for those of you perhaps who were not with us yesterday, to remind you of what we're talking about in this webinar, and that is deep borehole disposal. The difference between that and what I might call conventional deep geological repositories is that we're looking at considerably greater depth potentially for disposal of waste and different designs, including deviated boreholes. And we'll be hearing one presentation today, particularly aimed at deviated boreholes. So we're looking at depths of several kilometers now for disposal of some of the higher activity, most long-lived waste that we have to deal with. So you'll be seeing examples of this, and we'll be looking in particular at some of the technologies that have been developed and some of the thinking towards field trials for this solution. If you could put the next slide on, we can see what we're going to see today. The first presentation is going to be from Chris Parker of Deep Isolation, who's going to be talking about deviated borehole disposal. It's going to be followed by a presentation from Havard Kristiansen from Norwegian Nuclear Decommissioning, who's going to be talking about a project that's been carried out by the ERDO Working Group. This is one of the multinational working groups that I mentioned at the beginning, looking specifically at how deep boreholes could be used for small inventories. And then we'll have a presentation from Australia, from Dirk Mallants at CSIRO. Australia is currently thinking about how it will dispose of its intermediate level waste, and one of the options they're considering is deep borehole disposal. So he will tell us about some of the research that's going on behind this option. And then, as you heard earlier on, we're going to have a couple of inputs, I think, from our members of the Reliable Nuclear Fuel Services Working Group, comments on what's going on in their countries, and then we're going to open up the panel session. So if I could move over to our panelists for today to introduce themselves, and if you could just say a few words to say who you are. Chris, to begin with, please.
Yeah, hi. So I'm Chris Parker from Deep Isolation. I'll say a bit more about the company during my session, but very briefly, we're a private sector company set up in California during 2016 with a mission to deliver safe geologic disposal of nuclear waste, in particular by leveraging the innovations in directional drilling that have been pioneered by the oil and gas sector over the last decade or so. My role is Managing Director of Deep Isolation EMEA Limited. So that's a new subsidiary launched earlier this year with a focus on Europe, the Middle East and Africa. I'm based in London, And I should probably confess up front that my background is outside the nuclear sector. So I spent the first half of my career as a senior civil servant in the UK government, working on industrial policy and public sector reform. I then spent 15 years or so working with governments all around the world on a consulting basis, with a focus on development of public-private partnerships, nurturing new markets, managing transformational change. All of which very relevant, as it turns out, to deep borehole disposal, and hopefully we'll explore some of that further during the webinar. I've known Liz Muller, who's the CEO of Deep Isolation, for many, many years, been working with us since the start of the company, and that's now grown into this leadership role here in Deep Isolation EMEA. Looking forward to the session.
Good, thank you very much, Chris. We're looking forward to hearing your presentation in just a few moments. Havard, could you introduce yourself, please?
Yes, thank you, Neil. My name is Havard Kristiansen. I work for Norwegian Nuclear Decommissioning, which is a public agency for decommissioning 2 nuclear research sites in Norway and managing spent fuel and radioactive waste.
Thank you, Havard. And finally, Dirk.
Yes, thank you, Neil. So hello, everyone. Dirk Mallants here from the CSIRO in Adelaide, Australia. Great to be with you today. I'm a research scientist with a background in reactive transport modeling, currently supporting the Australian Radioactive Waste Agency with their low-level waste repository project. Previously, as Philippe van Mark, I worked at the Belgian Nuclear Research Centre, SEK-CEN, where I was involved with low-level waste and high-level waste R&D. That's me.
Great. So that's our panel for today. As I mentioned, they'll be joined later on by the panelists from yesterday for the closing discussion and looking at the questions that we posed. So let's begin. Chris, could you tell us about the Deep Isolation project, please?
Okay, sure. So if we could move on to the first slide. Right, I'd like to do 3 things today in my session. Firstly, just give a quick overview of Deep Isolation's technical solution and how it works. Then look in turn at what we see as 3 major potential benefits that this opens up for people charged with thinking about disposal of their country's nuclear waste. So safety, equitability, and affordability. And then finally, I want to share some of the preliminary results from work we're doing here in the UK, which is with our client, the Nuclear Decommissioning Authority, and hopefully that will be helpful in bringing to life what this technology can and can't do. If you could click on, I'm going to start with a very short animation, which I think is the simplest way to illustrate how this works in practice. So I think the next slide, if you open that and click run. Okay, so I'm showing here a disposal canister that's about 32 centimeters across, about 4 meters long, and we're looking at a BWR fuel assembly. It slips inside the disposal canister, we seal the edges. If you look at it from the end, you can see that's a snug fit. The canister itself, made out of highly corrosion-resistant alloys, the material should last for several thousand years. Now, we put it in deep rock. The rock can be sedimentary rock, as shown here. It could be granitic rock. It could be crystalline basement rock. It could be salt. This is a solution that works in many geologies. We begin by, excuse me, we begin by drilling a hole here at the top. So you can see the bluish area there, that's the aquifer. So we drill below that, then put down a metal tube called a casing, put cement down the middle of the tube. That's the gray material coming down there. That flows up the outside and gives us even added protection against anything reaching the aquifer. Now that's all standard procedure done on a daily basis in the oil and gas sector. We then drill further down. So here we're going deep into layers of rock, down to what's called the kickoff point, where it gradually starts changing the direction. A curve so gradual, if you're down there, you mightn't even notice it, until we eventually reach the horizontal. We go horizontally then for 1 to 2 kilometers, and then that's the region where we're going to put the nuclear waste. So we put cement down again, we put casing down again, just as in the upper level, and then we're ready to put in the nuclear waste. So here's a canister, a disposal canister with end caps on it. We attach several devices to the end. This one here is what's called the tractor, and you'll see that working in just a moment. We put this in shielding when it's above the ground to protect the workers, and then lower it slowly into the hole using a cable until it gets down past the curved area into the horizontal area. You'll see the wheels of the tractor expand in a moment. Yeah, there we go. And then we drive the disposal canister to the end of until it reaches a rest in the disposal area. Once that's done, we disconnect the tractor, remove it, pull it back up, and then we place another canister, and we repeat that process until all the spent fuel is in place. Once the canister is in place, we can then seal the hole with a range of potential sealing options depending on local geology and regulation. And within a few years, the enormous weight of the rock compresses those materials and provides an excellent seal to the narrow access hole. So now we've got the waste deep, and that isolated depth turns out to be very important to the safety case. I'll talk about that in a while. But first I wanted to talk a little about the range of repository designs that are available. So if we could click forward. Now in the video I've just shown, the illustration was a horizontal repository, which is probably the most striking illustration of the flexibility that directional drilling now gives us to develop the optimal repository architecture for a specific inventory and a specific geology. But as we've discussed throughout the webinar yesterday, there are a wide range of options are available. So directional drilling enables us to tailor the right solution for specific circumstances. That might be horizontal, but it might be vertical. For example, in the case in particular of a very small inventory, which needs only a small, relatively shallow disposal section. Or it might be some more complex geometry, for example, to work within the constraints of a specific location. From our perspective, as a company, our partnerships, our supply chain, our intellectual property, they support all of those. So we can work with national waste management organizations to deliver what's optimal for their needs. That said, as you can see at the sort of bottom right there of the slide, we do think that horizontal opens up some interesting new opportunities. So it delivers high levels of safety combined with cost benefits. And horizontal boreholes also have got some important passive safety features that address concerns that we know some governments have expressed in the past about borehole disposal. So if we click to the next slide, and just one more click, please, to bring up the points. Yeah. So on the left here are some of the concerns that we've seen get raised about borehole disposal. And none of these are manageable, and lots of good work has been done to address them within a number of deep borehole disposal implementation concepts. But on the right-hand side, I've shown how passive features that are integral to a horizontal architecture simply take that issue off the table. I won't go through all the points, we've got the time, but just to give a couple of points. At the top there is the question that all borehole disposal systems get asked. What happens if you drop a canister during emplacement? Now, in any sort of borehole design, there's no risk of the canister plummeting to the bottom at great speed. So the hole is filled with fluids, it's a very close fit. But in a vertical borehole, there will nevertheless be a significant impact at the bottom, and that just needs managing. In a horizontal repository, however, the drop canister will actually decelerate as it goes around the bend and just drift slowly to a stop. Similarly, looking at the example at the bottom, disposal canisters at the bottom of a deep vertical borehole are going to have significant pressures on them from the weight above. And again, that's manageable in a number of ways, but the horizontal solution is arguably the most elegant one. We just lie the canisters horizontally with zero pressure on them from any of the others. And finally, if you can click to the next slide, please. Costs escalate as we take a vertical borehole deeper. In a horizontal repository, though, cost increases tend to be much more linear. Clearly, total costs do increase as we expand the horizontal section from 0.5 kilometre to 1 kilometre to 2-3 kilometres, but they don't accelerate in the way that we see as we take a vertical borehole deeper and deeper. Okay, next slide, please. So where are we in terms of market adoption of the technology. Now, the blunt answer is that there is a lot of spent fuel and high-level waste in storage around the world, as illustrated on the chart here, and none of it has yet been disposed of in deep boreholes, whether vertical, horizontal, or anything else. The same is true of disposal in mined repositories. We've not disposed of waste yet, but it is clear for them that at least for a small number of countries, there's now a clear implementation path for the mined repository. Many others are struggling to follow that path because of the sheer scale of the cost involved. So boreholes offer a more affordable way forward, but how do we achieve that same clarity? If you could click on, please. From Deep Isolation's perspective, this is really about developing a global innovation ecosystem to tackle what is clearly a global problem. Part of that is the investment we're making in our own technology. We've now got over 40 different inventions around the 5 key elements of borehole disposal that are illustrated on the left, so formation suitability, repository design, etc. Grouped into 38 US and international patents granted and in development. And the majority of those support all the borehole architectures I touched on earlier. Some are relevant to vertical or horizontal only. Alongside this, looking at the sort of second pillar there, we're committed to sharing the underlying science we're investing in through open and peer-reviewed publication of that. Thirdly, we're developing a world-class supply chain, really trying to bring together the best expertise from the nuclear handling sector and the oil and gas drilling sector. So partnerships with organizations like Bechtel, NAC International, and Schlumberger, all leaders in their field, and our technical team works with them on a daily basis. Fourth, we see stakeholder dialogue and engagement as vital. We're looking to develop partnerships, mutual understanding with a very wide range of actors across academia, industry, civil society. But probably the most important part really is the fifth pillar on the end there, where we're looking to engage with potential clients and partners around the world. So in the ministries and government agencies that are accountable for delivering geologic disposal of nuclear waste in practice. Now, as the slide there gives some of the focuses really of that's engagement. So we're talking with governments to help understand what elements of their inventory are most suitable for borehole disposal, understand the geologic opportunities, mapping out regulatory pathways, and so on. I'll give an example of that sort of engagement when I look at the UK sort of NDA case study at the end. First, though, a very quick overview of the potential benefits from all of this. So if we could click forward onto the next slide, and one more. Okay, so safety. All the speakers yesterday emphasized the safety that comes from depth of disposal, and our research very much confirms that. So on the left there is one of the key findings from our published review on safety calculations for deep borehole disposal. And that shows that at depths of 1 kilometer or more, the inherent properties of many types of rock will keep radionuclides entirely isolated from the biosphere for millions of years. And when they do eventually reach the surface, so that's the red, blue, and green curves starting towards the right of that chart. When they do eventually reach the surface, the peak dose is calculated to be 1,000 times smaller than that deemed safe by regulators. So that's the blue arrow showing the difference in the chart. And that's a conclusion which is robust to change and robust to uncertainty. On the right there, I've illustrated how we've modeled hundreds of variant scenarios, each simulation running over a 10 million year period. Peak dose still remains orders of magnitude below standard, even in the most extreme scenarios. And a couple of examples there at the bottom. In the first, we've looked at the impact of complete failure of the disposal canister on day one, so instant mobilization of the radioactive waste. And in the second, we've modeled an extreme seismic event, so comparable to the San Andreas fault right up through the center of the repository. And in both cases, safety performance remains robust. Next slide, please. Secondly, borehole disposal offers significant potential benefits from the perspective of social equitability. Community engagement and consent is critical to success. It was central to the work we did in the siting process to locate our demonstration facility in Cameron, Texas, which is shown in the photo there. And our research, our sort of community research and engagement suggests that actually there were some specific features about borehole disposal that may help with the challenge that governments face in securing community consent for geological disposal. And that's really because boreholes are intrinsically a modular solution. And that opens up the possibility that the task of safely disposing a nation's nuclear waste can be shared across multiple communities rather than requiring just one large centralized facility. And that's potentially attractive from consent basis. So there's some evidence that communities that have benefited economically from nuclear power generation may feel that it's fair and equitable for them to dispose of their waste as they see it, whereas they might be less ready to host a nationwide inventory. Also on the right-hand side of the slide here, I think that's an important issue around generational equitability. Again, yesterday, several speakers emphasized the fact that borehole disposal can be implemented much more rapidly than the decades process of designing and constructing a traditional mined repository. We agree, this is a solution that our generation can and should implement rather than continue leaving nuclear spent fuel as a problem for future generations to deal with. Next slide, please. So last but not least, borehole disposal is significantly less expensive than disposal in a traditional mine facility. We published case studies showing estimated savings of between 50 and 70%. And that's driven by lower costs at every stage of the repository life cycle. And to be honest, we and our partners in developing those costings have sort of layered caution upon caution in our assumptions. We think we can actually deliver for significantly lower costs. Second point on the slide there is that the risk is lower. The risk of budget overrun and so on is lower, because the bulk of the cost for construction of a repository for disposal of spent fuel in particular are based on off-the-shelf technologies that are delivered, used on a daily basis in the oil and gas sector. So for much of this, we're talking about pricing out of catalogues, in effect, very different from the huge, complex, bespoke engineering projects that are inevitable for a mined repository. Okay, so last part of my talk, if we can move on to the next section. The UK, how all this sort of comes together in one country. So for the last 8 months or so, we've been working with the Nuclear Decommissioning Authority to explore how this technology might apply in the UK context. That work's nearly finished. We hope to publish it soon. And I should stress that no decisions have been made yet by NDA, by the UK government about the technology. They have kindly agreed that I could share some of the headline findings today. So if we could click to the next slide. Okay. So the first conclusion is that only 11% of the UK's inventory for geologic disposal is really suitable for disposal in boreholes. And that raises the question that Neil brought up yesterday. If as a country you're going to need to build a mine facility anyway, why bother with boreholes for just some of that? But if you can see the breakdown of waste streams over on the right there, the 11% which we found is suitable covers all of the high heat generating wastes. So that means that although it's a relatively small part in terms of the package volume, 11%, it's extremely interesting. In terms of the UK's plans for a mined repository, that 11% takes up a much greater share of the overall cost and the physical footprint of the repository. Secondly, we've looked at the safety performance of this technology and mapped that against the UK's published generic safety case for geologic disposal. Now you clearly can't see the detail on the table there, but it's basically an assessment matrix summarising the safety evidence against three sort of life cycle stages that are used in the UK's generic safety case, so transport safety, operational safety, and post-closure environmental safety. And then map that vertically. The columns are looking at the three major geological environments here in the UK, so lower strength sedimentary rock, higher strength rock, and evaporite.
About 15 minutes, Chris.
Okay, I've got just one more slide after this, so I'll wrap up quite quickly. Key conclusions in terms of safety is that broadly the solution is aligned with the UK's requirements. Further evidence and demonstration needed in higher strength rocks in particular, that's the amber cells there. And also, again, as we discussed yesterday, more work needed on documentation and demonstration of the safety case, in particular in the transport and operations stages, where that documentation is still not been done yet, but there's no real reason to believe it can't be managed safely. We looked at 15 scenarios in box 3 there for costs, looking at all of that, the high heat generating waste, so the 11%. Costs were ranging between sort of $1.9 and $2.6 billion, and we also looked at costs for a subset of waste streams within that. Finally, point 4 there on the slide, as you'd expect, still lots of questions to answer, and we've started to map out the further work and analysis that's needed across a range of regulatory, social, geological, and operational issues. So that's work which is going to get published, hopefully not in the not too distant future, and I think will be very relevant for this audience. So to conclude, final slide, please. The context for this, I think, has to be a recognition that we have not yet disposed of any of the spent fuel we've generated over the last 70 years. And our view is that the current model for geologic disposal is simply not scalable. I've got nothing but admiration for the countries which have gone furthest in bringing this to a reality. It's a huge amount of work that's been done. But these large centralized facilities that take decades to plan and deliver and are hugely expensive, we don't see as a scalable way forward. On the other hand, directionally drilled borehole repositories offer a feasible, scalable, safe, affordable solution. The technology to deliver this exists now. Lots of work on how we, as it were, bring it to fruition in the marketplace, and Deep Isolation is committed to working with all of you to make this happen. Thank you very much.
Thanks very much indeed, Chris. Lots of interesting food for thought there. One of the things that occurs to me, of course, is that with deep vertical boreholes, one of the advantages is a very small footprint. And if you're going out horizontally, presumably that has some implications for land ownership and so on that you might have to consider. Is that something you've thought about?
Yeah, it is. I mean, clearly the footprint horizontally, if you've got a sort of 1.5 to 2 kilometer horizontal extension, then that's by definition a bigger footprint. Those physical footprints are smaller than we're talking about for a mined repository underground, and very significantly smaller above ground. Mm-hmm. But yes, clearly those issues about land rights and so on are important ones, as they are for any form of geologic disposal.
Great. Any other comment from the panel before we move on?
I had a quick question, Neil. Chris, relative to demonstration, you mentioned the Texas site you have. Could you, obviously oil and gas doesn't emplace stuff and bring stuff back up. Could you speak at all to what so far has been demonstrated relative to disposal approaches?
Yeah. So what we've demonstrated at Cameron is so we used a small diameter disposal canister. We we demonstrated the emplacement and retrieval process. So that's, and we did that without nuclear waste. Yeah, so it's the disposal canister, so without nuclear handling as part of the demonstration. But what we did demonstrate is how you can emplace that canister, leave it safely in a horizontal storage disposal section, come back out, and then go back in and retrieve that if you want to come and get it back out and have a look at it. So that's the key focus of our initial demonstration work.
Good. Well, thank you very much indeed. One thing maybe you could generate a number for us when we come to the final session was the disposal cost per tonne for spent fuel from that UK study. I'm not asking you immediately for it, but it'd be interesting if you have actually estimated that, and we can discuss that later on.
Okay.
Thanks, Chris.
Carl was also raising hand.
Yes. Have we got time for a question?
Yeah. Mm.
Right. It's a comment on slide 6, Chris, where you mentioned some of the risks of traditional, well, not traditional, but vertical deep boreholes. My comment is that some of these criticisms are a little unfair now because they're a bit out of date. Let me just give you an example. You mentioned the crushing risk. Well, if we use a high density support matrix, like what I talked about yesterday, which gives a slightly slightly negative buoyancy for containers, you alleviate some of that axial load. And we've also done some stress analysis quite recently and showed that the crushing stresses or crushing forces from the low over for the stack of containers is offset by the crushing forces of the local pressure. So I don't think it's as bad as what it's portrayed. And sealing, obviously rock welding, that would sort out the sealing risk. You still have a vertical section in your deviated boreholes, so you've still got a risk there for vertical transport. That doesn't go away. You mentioned dropping canisters. Well, we've done some small scale experiments dropping heavy cylinders down a water-filled tube, and so have Sandia. We've done modelling work, and terminal velocities of canisters are only 1 to 2 meters per second. So it's very small.
So Carl, I mean, I agree with everything you said there. I think you know the word unfair is reasonable about some of those criticisms. They are there. That's you know when we talk with people, these sort of things are and in some cases, you know, governments publish this sort of thinking as why they're not interested in pursuing boreholes. I think the only point I was really trying to make from that is, you know, these things are you know, they're not as significant as people have often sometimes in the past said, and they're manageable. They are more manageable, but there's a sort of, you know, elegance, as it were, in the geometry of the horizontal borehole, sort of as a simple and almost cost-free way of addressing some of those what are concerns in the marketplace.
Indeed, Chris. Perhaps the time is right, in fact, for now assembling some of the arguments that address some of these concerns and issues that have been brought out. I mean, we now seem to have plenty of information available to us to begin to do that. So maybe that's something we should think about towards the end of this webinar. Okay, I shall move on now and ask Havard Kristiansen to tell us what's been going on in the ERDO project run by Norwegian Nuclear Decommissioning.
Thank you, Neil, and thank you to IFNEC for allowing me to talk briefly about what we are working on here at the NND and within ERDO. Next slide, please. So ERDO was originally established as a working group for waste management organizations in European nations with relatively small amounts of radioactive waste. But in the last year or so, we have been focusing more on sharing competences and studying solutions which we may have a mutual benefit from. And borehole disposal is one such solution. Next, please. Next slide, please. Thank you. So the borehole project that we are conducting in ERDO, the purpose of that project is to describe one or more borehole concepts and assess how that might be used for the waste inventories that the participating nations have. And as it happens, this covers both high-level waste and low and intermediate level waste, but I will only be talking about high-level waste here today. And today I'll briefly describe the central component of our reference design, which is the canister, and the compatibility of the waste inventories with that canister. I'll provide some simple cost estimates and discuss more broadly about what affects costs, and point out a couple and especially one strategic implication of borehole disposal. So next, please. So one thing we have learned is that when you design a borehole concept, the canister is really the central element. And for high-level waste, we have selected the canister shown on the picture here as our reference design. It is 5 meters long and approximately 52 centimeters wide. And the reason why we have selected this canister is that it can take both spent fuel and high-level waste from reprocessing. Next, please. So on this and the next following 3 slides, I will present the inventories of high-level waste that we consider in our project. First are Croatia and Slovenia, who share responsibility and ownership of the nuclear power plant in Krško. It is in operation, and it has been estimated that during its period of operation, it will generate about 2,282 assemblies of spent fuel. And with our canister, you would need the same number of canisters to dispose of those fuel assemblies. One thing I'll point out right away, however, is that our canister is not ideally suited to those fuel assemblies, as you can see on the right-hand side of the screen there. The canister it doesn't fit as snugly as we could see in the canister on Chris's presentation. So by selecting a narrower canister, as we will discuss later, one might reduce costs. In the following slides, I will only be talking about the spent fuel from Krško. However, Slovenia will have to handle spent fuel from 1 research reactor. That's a very small amount compared to this spent fuel. And there will also be what has been classified as high-level waste from decommissioning of the power plant and from the foreseen operation of an encapsulation plant. But those wastes have been planned to put in so-called high-safe containers, which are too large to be put in a borehole. So next, please. The next country is Denmark, which has a much smaller inventory of high-level waste. Denmark has had 3 research reactors in operation, and the spent fuel was returned to the country of origin, with the exception of 233 kilograms of residues from post-radiation experiments, which remain and which need to be managed. And one could discuss whether this waste really qualifies as being named high-level waste. It is not heat generating, but it is termed a problem waste in Denmark, and a solution needs to be found. This waste would have to be put in, you would need 7 canisters to dispose of this waste in a borehole. Next, please. The Netherlands, on the other hand, has by comparison large volume of high-level waste. There's 1 nuclear power plant in operation there, and they have had 1 more previously, which is now shut down. There are also 2 research reactors, which are in operation, and 1 that has been shut down. And the Dutch strategy is to store waste until the year 2130, while they look for permanent solutions and allow decay of the waste. Now, the strategy for the commercial spent fuel is to reprocess it. That has been estimated to generate a total of 1,078 canisters of reprocessing waste in 2130, which would require 359 of our disposal containers, because you can put 3 canisters of reprocessing waste in each borehole container, as is shown on the small figure there. The high-level waste from the research reactors is planned to be put in what's called ECN containers, which are shown on the bottom right there and are too large to go in our borehole. Next, please. The final country that has high-level waste in our project is Norway. That's spent fuel from 4 research reactors, which all have been shut down now. And this would need 69 containers to be disposed of. Next, please. So this figure just shows that about half of our high-level waste could go in a borehole and about half could not. And as Chris was talking about, borehole disposal may nevertheless be of interest. One argument is that if you put the high-level waste in borehole, then the requirements and the design of your mined repository may be simpler. There's also a timing perspective here. Maybe you can dispose of the borehole compatible waste earlier and then have more time to design your mined repository. And those processes could take a different amount of time. Next, please. Now, the next subject I'll talk about are costs. And the key finding about cost is that the costs really depend on the design, which in turn depends on the waste form, the size of the waste inventory, the geological conditions, and the safety requirements for your disposal facility. And if I start on the top left there, if you have optimal geological conditions with shallow formations with low permeability, competent and drillable host rock, then you can dispose of your waste fairly close to the surface. And that's significant because the costs of a vertical borehole increases exponentially with depth. And on the lower portion of the screen there, wider holes are more expensive than narrow holes because they need bigger rigs for casing strings, etc. On the other hand, wider holes can accommodate larger waste packages and therefore more waste per unit length. And another factor that you have to take into account is that you need to design a repository that is custom for your particular waste and its radiotoxicity, its chemical and physical properties, the mobility of the particular radionuclides in your inventory. All of these factors impact the safety requirements of your repository. And then finally, since we are at the very early stage of developing or looking or considering developing a borehole disposal facility, there are uncertainties in the safety requirements and that affects your design and that finally affects your cost estimates. Next, please. So I'll try to do this rather fast to not use too much time, but mostly to illustrate this uncertainty, I have defined 3 different borehole profiles. A is 3.5 kilometers deep vertical borehole, where I have assumed you could put waste in the lower 2,000 meters. So you would have 1,500 meters for seals and backfilling. B is a shorter borehole, it's 2 kilometers deep, and you could put waste a little closer to the surface here. You have a slightly more suitable geological conditions. And then C is a very short borehole, it's 1,000 meters deep, and you could put waste in the lower 100 meters. So we have some variables there for the borehole design. There are also at least 3 more variables. Those are the cost of each borehole design, which is the 4th row in the table on the right-hand side there. And then there's a variable concerning how closely you can space your canisters. Like Carl was pointing out, you probably will put some material between canisters to support them and protect them and work as a secondary barrier in case your canister fails. But how much, we don't know, and how much you put in affects how many canisters you can put in each hole, so which in turn affects how many holes you need for each nation. And then there's the final variable concerning how much it costs to place each canisters. And we've assessed this for each country with a Monte Carlo simulation, and the results of that is shown on the next slide, please. Here we go. So I'll go through this quickly. For Croatia and Slovenia and the Netherlands, on the top left and the top right, we can see that the larger boreholes are the most cost efficient, which is no surprise because you would expect that from simple economies of scale. But we should remember that the Croatian and Slovenian costs are probably a little high because we have a suboptimal canister design. Interestingly, for Denmark at the bottom left, if one could find optimal geological conditions, a short borehole of only 1,000 meters could enable Denmark to dispose of their waste for, well, something on the order of tens of millions of euros, which is very little. Whereas for Norway on the bottom right, the 2,000 meter concept is the most cost efficient because 5 to 7 boreholes of 1,000 meters length would be required. Next, please. Another interesting finding from an ERDO perspective is that because of the modular nature of borehole disposal, sharing one multinational facility is not necessarily very cost saving. Here I've added up the costs of the individual nations and compared that to a shared facility, and you would only save about 6%. And this, of course, is connected to the fact that you have to design a concept that fits your particular wastes, which I've already described. Next, please. Neil, here I have the numbers that you requested from Deep Isolation, by the way. But what I wanted to do here was compare our cost estimates, which are the top 2 rows, to other published costs. And one observation is that our cost estimates for Croatia and Slovenia, which have the largest amounts of spent fuel, are in fact about 1 order of magnitude larger than the lowest cost estimates for disposal of spent fuel in boreholes. You could explain that with the suboptimal canister, which causes you to have a large diameter. And there are some economies of scales here and different costing methods. And it's worth remembering that our canister is designed to take both reprocessing waste and spent fuel. Next, please. One thing that I have not covered in my cost estimates is encapsulation. And encapsulation costs a lot if you want to do it in the KBS3 way for a mine facility. Here I have some images from Posiva in Finland. It requires a lot of competence. It could be very costly. And a key point here is that we don't know if a borehole canister would have to be designed and sealed the same way as you would need in KBS3. But if you do, then perhaps encapsulation could be an area of interest for national collaboration, or for commercial enterprises who could perhaps sell this to nations, sort of the way reprocessing has been done in the past and indeed still is. So next, please. Yeah, this is my final slide, and I'm not sure how I'm doing on time, so I can stop here if that's needed, Neil.
No, you've got a minute. Carry on, Havard.
All right, thank you, Neil. Well, my take-home messages are that the cost of your disposal facility and your design really depend on the design. And that should be determined by the waste that you are looking to dispose of, how large each package is, how much waste you have in total, where you want to build your disposal facility and the conditions there, and which requirements are put on your disposal facility. So in short, how do you build your safety case? Yeah, that's actually both of those on the left-hand side there. And then interestingly, maybe borehole disposal could enable small inventory nations to implement geological disposal independently at a manageable cost. But if borehole disposal becomes an available solution, then the question of encapsulation needs to be looked more closely into, and this could open up new opportunities for multinational collaboration or commercial enterprise. Thank you.
Thank you very much indeed, Havard. There's lots of interesting information there. We've had a lot of interest in, particularly on the cost side of things. I mean, it's often said that disposal of spent fuel in a deep geological repository works out at around $1 million or €1 million, say, a ton. You're showing prices there or costs there which are considerably lower. And I'm wondering if one of the things you might move on to would be to look at the modular cost savings you get on a geological facility if you're able to take out some of these wastes from the GDF. As we've said, several of us have said, you know, the requirements on the repository might be considerably less if you're able to remove these wastes. So there might be cost savings at both ends of the scale.
Yeah, I believe you're right. I think for the Netherlands and for Croatia and Slovenia, if they were to dispose of their spent fuel or reprocessing waste in boreholes, then their geologic disposal facilities, or their mined repositories, as I prefer to call them, could be less costly. They would not need to include rather sophisticated elements that you have in, such as the KBS3 concept.
Mm-hmm. Indeed. Any comments from our other panel members here? Yes, Jeff.
Yeah, so this isn't so much a question for Havard as just a comment or an observation on costs. All of these cost estimates are very useful. Both, you know, Chris presented some and Havard did, but I guess we should all keep in mind that the ultimate cost of disposing of waste, whether it's a mined repository or a borehole, includes the siting, the regulatory, and the licensing costs. And often those costs are quite significant compared to, you know, just the pure operating and engineering costs. You know, I mean, we spent $15 billion on Yucca Mountain and didn't emplace anything. So just a reminder, not that all these studies are not useful and shouldn't be considered.
Yeah, I could just point out that for the 1,000 meter concept, those costs included site investigation and closure. Of course, it did not include the holistic consideration of different regions and the possible effects of delays due to regulatory or political processes. So this was assuming, you know, a smooth process.
And of course, that was one of the questions we had for the panel. It was, you know, what would it take to bring deep borehole disposal up to a similar level of regulatory approval? How is it going to be more complex or more time consuming to do that, given that it's, you know, it's got a bit of development way to go yet?
Neil, just to add that our costings take the same approach as Havard's, so including citing, site characterization, etc., but with a similar sort of assumption about, you know, relative smoothness of the process.
Right. Okay. Lots of interest there. Lots of cost numbers. It's the first time we've really seen. Do I hear a voice there?
Neil, yeah, I just wanted to ask one question.
Sure.
Havard, did you look at using deep borehole disposal as a complement to a repository program, or was it just as an alternative? For example, if you had different types of waste, would it make sense from your studies to, from an economic perspective, to use a deep borehole to dispose of some versus a repository? Or do you think the cost would just be prohibitive to be running parallel programs like that?
Well, I don't think this is part of the ERDO study, but we are discussing such questions in Norway for our waste because we have a need to expand and modernize our existing infrastructure for radioactive waste, including establishing a repository for high-level waste, which does not exist, and then building a mined repository together with a mined repository for building one for high-level waste together with one for low and intermediate level waste could be more competitive with borehole disposal than building if you build them separately. So I think that's also one element. It really depends on whether you want to just dispose of high level waste or if you need to really build one, what we call a national facility for all types of radioactive waste.
Good. Thank you very much indeed, Howard. I'm sure these things are going to come up again later this afternoon. We're going to move on now to Australia. As I mentioned earlier on, Australia hasn't decided yet on the pathway it's going to take for disposal of its intermediate and longer-lived waste. But one of the things that's of interest is deep boreholes, and Dirk is going to tell us about those.
Thank you, Neil, and hello again, everyone. So for those of you that dialed in a bit later, I'm Dirk Mallants from the CSIRO in Australia, and I feel really privileged to be given the opportunity to present our project to you today, with special thanks to IVNEC for the invitation. Now, our deep borehole demonstration project is a partnership between CSIRO, and we are Australia's national science agency, the Sandia National Lab in Albuquerque, New Mexico, US, and ANSTO, the Australian Nuclear Science and Technology Organization. Now, before I start, I'd like to acknowledge Tito Bonanno, Jeff Rees, Pat Brady, and David Sassani, all from Sandia, who were instrumental in putting together this borehole demonstration project proposal. Next slide, please. So the purpose of this exciting project is really to demonstrate technical feasibility of borehole disposal for a variety of waste forms, including intermediate level waste and high level waste, and identify the conditions for long-term safety. Now note that Australia currently does not have high level waste and is not likely to have any high level waste. So any reference to spent nuclear fuel in this presentation is for the sole purpose of offering potential R&D solutions to other countries, and in this way help progress their domestic disposal challenges. Also, there is no decision yet in Australia that deep borehole disposal will be the preferred way to dispose of intermediate level waste. We are currently considering as an option, but one which makes sense, I guess, when you have only a very small volume that's to go deep underground. Now, to achieve this, our deep borehole demonstration project has 4 work packages. And work package 1 is all about near surface waste emplacement testing using dummy waste containers. This will still be at the engineering scale in a rather shallow hole to test all procedures before moving to the full scale test. Now, when our testing at the engineering scale is complete, we're roughly at technology readiness level 6. See the graph below. Work package 2 is about developing and testing novel waste forms and disposal canisters. Work package 3 involves development of several enabling technologies. And then work package 4 is the final integrated waste emplacement test in a deep, large diameter vertical borehole. That is a full scale test, which when completed, brings the entire system to TRL 7. This is probably similar to cold commissioning of a conventional DGF, which is one more step required at this hot commissioning before the system can become operational. So I'll now walk you through each of those work packages. Next slide, please. So the first work package is about the initial waste emplacement test. Note that there's basically two types of emplacement tests. The first one is a near surface test in a shallow hole, maybe up to 100 meters, followed by the final test in a very deep borehole, and that is work package 4. Next slide, please. So the waste emplacement equipment that we will use is shown here, and it is based on a design by German company BGE Technology. They manufactured this about 10 years ago and successfully tested it under typical engineering scale conditions in a 10-meter deep artificial hole, and you see that in the top left image. So the test components are as follows. There is a dummy or cold disposal container, which is about 5 meters long, shown in the top right image, which is transported from a storage facility to the borehole in this orange 45-ton transfer cask, which is then moved into the blue canister lifting gear, which will bring the transfer cask in a vertical position. There's a canister grabber connecting to the hoisting cable that will grab the canister and lower it into the hole to the required depth. Now, the real challenge will be to undertake this testing in a, let's say, 2,000-meter deep hole filled with a mixture of fluid from drilling and formation, and also test, of course, canister recovery and the emplacement of seals. Now, the good news is that BGE technology has proven it works at very shallow depth, so we're confident that it will also work at deeper depths. Next slide, please. So the next work package focuses on the testing of the Synrock waste form and development of what could be a one-size-fits-all disposal canister. Synrock or synthetic rock is a waste form that was developed by ANSTO originally to treat as liquid waste streams from molybdenum-99 production. So Synrock can be a ceramic, glassy, or a ceramic glassy waste form. Synrock will be tested for plutonium wastes, potentially waste from Gen 4 reactors, and potentially waste from small modular reactors. However, as I said in the beginning of my talk, this is only to assist other countries with progressing their domestic disposal projects. As it stands today, Australia will not dispose spent nuclear fuel. Now, we'll also specifically study this waste form and waste form alterations under borehole specific conditions. So that means looking at some uncommon geochemistry at great depth, combined with typically high temperature and pressure. However, having a proper waste form is not enough. We also need a disposal container. So the idea is to develop this one-size-fits-all that can accommodate, in the first instance for Australia, the CSDU canisters with vitrified intermediate level waste, and then the Synrock packages, which come out of a hot isostatic press. And a candidate canister in stainless steel is the one designed by Guido Bracke and his colleagues in Germany. We'll also be testing coatings that can extend the lifetime of such containers by using CSIRO's cold spray technology, where we can deposit a copper or titanium or any other metal coating using a supersonic spray system that is shown in the bottom right image. Next slide, please. So throughout the project, a number of novel enabling technologies will be developed that will assist with the development, implementation, and testing of the borehole concept. And it will not be a surprise that borehole sealing materials are at the top of our list, as the borehole itself is the only potential major radionuclide migration pathway. Now, we will study bentonite, its behavior under conditions of high temperature, pressure, and potentially some unique geochemical conditions as well. So we will do some practical tests of seal emplacement, for example, based on a concept for sealing monitoring boreholes developed by SKB, where copper perforated baskets, shown in a top graph, were delivered or would deliver pre-compacted bentonite down to depths of about 500 meters. And this was done to reduce erosion while pushing the bentonite through a fluid-filled hole, where the bentonite itself has an organic coating that would gradually dissolve and thus allow for controlled swelling, and in this case, not avoid blockage of the hole due to early swelling of the clay. We need advanced rock sensing tools that can reliably work at great depths, potentially again under high temperature. Robotics equipment will be needed for waste handling during waste emplacement. And for the monitoring of the borehole seals, we'll need some novel tools, including potentially fiber optics that have been successfully used for distributed temperature sensing in deep exploration holes, or wireless sensing and transmission devices such as these pressure transducers in the bottom graph. And to prepare for the next step, that is to select a site for final disposal once demonstration has been completed, we aim to develop a machine learning-based site screening software for unbiased site screening. Next slide, please. So the final work package, which is really the cherry on the cake, is the integrated waste emplacement testing in a large diameter deep borehole. This involves a full-scale demonstration test where we will first drill a 2,000-meter deep characterization hole to study the rock and all its facets, then drill the large diameter borehole, do the waste emplacement testing using the modified PGE technology, and then we'll do the seal emplacement testing. We'll also continue our performance and safety assessments, considering a variety of waste forms, waste types, with the proper set of scenarios, and then we'll synthesize that in a safety case. And the time scale for this project is from mid-2021 to mid-2028, pending successful funding arrangements. Needless to say, of course, that this is something we cannot do alone. Hence, this will be a multi-organization collaboration of which key partners are listed here, the CSIRO, ANSTO, Sandia, with technical support from BG Technology. There's going to be a waste emplacement manufacturing company involved as well. And as you can see, there are still some vacancies in the collaboration wheel. So if people want to know more about how they can get involved, please contact us. Next slide, please. So in preparation of the borehole demonstration project, we have started some generic safety assessments. And one of the reasons for doing so was to understand the effect of disposal depth on the radiological impact or dose, and indeed, how deep do we really need to go? Is it a kilometer, 3, 5 kilometers? So we developed a 3D numerical model as the basis for the assessments. It has a number of components, including the inventory made up of 100 CSDU containers, and we assume they'll fit in a single hole. We test the effect of 3 disposal depths on those. And there's a rather shallow hole from 300 to 500, and 800 to 1,000, and 2,800 to 3,000 meters. The model has 3 geological layers. There's a regolith from 0 to 25 meters with a high permeability. Then there's a weathered basement rock from about 25 to 100 meters with medium high permeability. And finally, we have the unfractured basement rock from about 100 meters onwards with low permeability, and groundwater flow occurs only in the top 2 layers. We also tested the sensitivity of radionuclide migration with respect to permeability. So both 100 times higher and 100 times lower values were used. And a sensitivity analysis was also done for radionuclide sorption on the various materials. And also here, a range of values were used. And finally, the assumptions about the waste form and engineered barriers are quite conservative. So we assume instantaneous release, all radionuclides, no engineered barriers at the disposal zone. And the only engineered barriers are the cementitious and bentonite seals above the disposal zone. And a snapshot of the results is shown in the top graph for the shallowest disposal depth, that is from 3 to 500 meters. The animal dose is shown at a hypothetical well for 4 typical radionuclides. And the peak dose for selenium-79 and technetium-99 is about 10⁻⁴ millisieverts per year, which is 4 orders of magnitude below natural background dose in Australia. Peak dose for tin-126 is about 3 orders of magnitude below that. And finally, plutonium-239 is again 1 order of magnitude lower. And then the bottom, or the effect of both larger and smaller rock permeabilities, is shown in the bottom graph using these blue bars. Each bar represents the dose variation due to a 4 order of magnitude range in permeability, with the little vertical bar indicating the best estimate value. So clearly higher permeabilities, of course, will increase the dose as transport time through the host rock will be faster, just less opportunity for radioactive decay. But importantly, all doses are still much smaller than the background dose. At 1,000-meter depth, all doses are, of course, much smaller, so small even that they become physically meaningless. Anything less than 10⁻⁷ meters per millisieverts per year is, in fact, meaningless. Purple bars show the effect of high absorption on the relative to the blue bars. Assumptions of high absorption clearly results in a significantly reduced dose because of the retarded transport times, allowing for additional radioactive decay. And where there are no bars, the dose is less than 10⁻⁴ millisieverts per year. So as we speak, we are continuing calculations for also sedimentary rock looking at other scenarios, more realistic models for waste form and engineered barriers. Next slide, please. So we have also developed, yeah, I'm almost done.
Thank you.
We've also developed a state-of-the-art analytical capability, confirm that the rock at the disposal that are devoid or free from fresh groundwater. So this means that there hasn't been any flowing groundwater for a long time, and there has been, and therefore the rock provides proper containment, which is of course an important criterion to select a site for borehole disposal. And we can now also measure noble gases at fluid inclusions by extracting these gases under vacuum and then send them to a mass spectrometer using this vacuum crusher. Next slide, please. And this is the second of our noble gas facility, which is the ATA or atom trap trace analysis facility, where we measure radiokrypton and radioargon, especially krypton-81 is again an indicator of old groundwater. And we will use both facilities to demonstrate tightness in the rock. Final slide, and these are my take-home messages. So first of all, many of the key components and technologies for demonstrating deep borehole disposal are available or need some but limited modification. Now, while a full-scale integrated test with drilling, waste emplacement, sealing has not yet been undertaken, we are confident it is achievable in a 7 to 10 year time frame, with a 10-year including both hot commissioning. The next one is a no-brainer. International experience and collaboration, of course, should lessen the technical challenges. And finally, when we've completed the demonstration test, not only will we have new tested and validated way to dispose of our waste, we will also have the technological and scientific spin-offs that are, of course, inevitable with such large multidisciplinary efforts. I mentioned only some of the more obvious spin-offs, such as this new water and rock age dating techniques, technologies to support in-situ mining, better ways to emplace seals for oil and gas, CO2 geosequestration, and the like. And that's it for me. Thank you, and happy to take questions.
Thank you very much indeed, Dirk. Very exciting prospects for this new project over the next few years. One quick question from me. Do you have a target geological environment for your field test? Or are you thinking of sediments or basement rock, or does it really matter?
For now, all the options are open. We will be looking at 3 potential geologies: crystalline rock, granite, sedimentary rock, mudstone or clay rock, but also rock salts. We have significant rock salt formations in Australia, up to 800 meters deep. In the Canning Basin in Western Australia, there's about 100,000 square kilometers of these. So we're looking at each of those. And the plan is that in the first year of the project, we will be focusing on 2 or 3 geologies, try to collate site-specific petrophysical properties and other properties, do more detailed safety assessments, such that we can, at the end of the first year, make a choice where we will undertake the test. There's of course another parameter which is important, that is you need to have a willing landholder. So in parallel to the scientific investigations, we're also talking to a number of agencies and state governments to explore if they're willing to host this demonstration test.
Great, thank you. Chris, did I see you raise your hand there, or was I imagining it? Obviously imagining it. Anybody else have a quick question here for Dirk before we move on? Okay, well, thanks again, Dirk. Don't go away. We've got certainly some points that we'd like to pursue further with you in the panel session later. Before we move there are a couple of contributions from members of IFNEC's Reliable Nuclear Fuel Services Working Group. I understand that Alexander Bichov from Rosatom would like to say something, and Leon Kegel from Arau in Slovenia. Are you out there, and can I invite one of you in?
Okay, so thank you very much, Neil. So are you listening to me? Yes.
Yes, we can get you.
Okay, thank you, colleagues. Really, it was a very interesting webinar and highlighted a lot of aspects of this technology. But I would like to share some experience in my country. Till by joining of IAEA, I worked in Research Institute of Atomic Reactor in Dimitrovgrad. It's a key Russian site for research reactors and some post-radiation studies, fuel cycle, and so on. But this site has very unique technology, deep well injection of low-level liquid radioactive waste in on the. It's about 1,400 meters, 1,500 meters, limestones with saturated water. And in 1990s, so 20 years ago, we start some consideration of using of old hull, old wheel, for disposal of high-level radioactive waste or some residuals after post-radiation examination, and accidentally spent fuel from research reactors. We, in our institute, this study was led by Professor Yuri Chechotkin, and we found that from a technical point of view, really it is possible to use this hole for disposal of radioactive waste. But after evaluation of safety and other things, we met another problems. From point of view of Russian system of count and control of radioactive wastes and high-level radioactive wastes and spent fuel, we cannot receive any type of license for disposal of this type materials by this technology. Of course, it is one point, and of course, in our country we have a good established system of radioactive waste management, and so for countries type of Russia and the similar countries with similar system, it's not reasonable, not only from point of view of licensing, but from point of view of overall costs. We have good established system for reprocessing of spent fuel of research reactors. We have good established system for collection, accounting, and disposal of radioactive wastes. So, of course, we close our internal program. I underline it was program of institute, not as some national program. But later, now I would like to highlight another aspect. During last 5 years, sometimes I work as some expert for analysis of some newcomers' national spent fuel and high-level waste strategies. And also some newcomers try to consider borehole deep geological disposal technology. But here it's also a lot of specific points. First of all, this technology cannot be considered in current safeguard approaches. Here is we can locate spent fuel in some uncontrolled system, and so till now the agency has no approaches for safeguard control of similar systems. But for radioactive isotopes, for high-level waste without fission products, of course, this technology can be considered for some other countries. And third, small remarks, maybe it's remarks from outside of our community. Many people are considering the borehole disposal conception as some dispersed approach. The whole in different places. But I think for it's very important to underline that for some cases, for for example, cases discussed my colleague today's, its technology can be used in some centralized system in some one place. And for example, if we can find good underground geological repository conditions, we can use a number of holes for disposal of some limited wastes. Okay, so it's my 3 points. Thank you very much.
Okay, this is Leon Keger speaking.
Okay, Leon, sorry, I was muted there. You didn't hear me calling for you.
Yeah, but you can hear me now, right?
Yeah, I can hear you.
Okay. Thank you for all the presentations. It was quite useful and excellent to see that deep borehole disposal is developing quite fast. I would like to present some kind of insight from the small inventory country with the spent fuel from research reactor and nuclear power plant. In Slovenia, we have not explored deep borehole disposal concept or this option very deep yet. Just a small part was done with the ERDO Working Group, what was presented today by Havard. But we plan to work on this more in the future. And as a small scale nuclear program that is generating high-level waste and spent fuel from research reactor and nuclear power plant with a limited inventory. We would like to include in next year's this option into the national strategy, as our implementation of the disposal in national disposal facility, which is for now mined deep geological repository, is quite far away in the future. That's why we are very open to also some other alternative options. And certainly we see a lot of opportunities and advantages for optimization in this regard, but not only for domestic or national disposal facilities, but also for the option of regional or multinational disposal, especially if we focus on small inventory or early stage nuclear or disposal programs. Therefore, I'm very excited about this option in next years, what will be done in this and how things will develop. But still some very not clear decisions we need to take, and there are a lot of really opportunities we have to solve and challenges. But I can see that this could be one of the options that can help also small inventory countries. Thank you.
Thank you very much, Leon. It's good to see that there is interest now growing in this in a number of places. I'd like to move on to the panel session now. If Danielle, you could put up the last slide on the slide pack, which has got the questions that we'd asked the panel to look into yesterday. And as yesterday, I'm not going to read them, and I'm not going to run through them necessarily in order. Some of the panelists have already said they'd be keen to say a few words about some of these. I'm actually going to move directly to question number 5 on here, whether it's correct that deep borehole disposal opens up a much wider range of siting options than conventional deep geological repositories. And Fergus, I know you had something you wish to say about this. If you could say a brief word, that would be good.
I suppose the answer to this is yes. Certainly for the very deep holes. For holes less than 1 or 2 kilometers, perhaps a bit less so. But from the technical perspective, the key criteria for borehole site selection are, as we've heard from everybody, the stable host rock with very low bulk hydraulic conductivities, a low anisotropy, regional stress regime, and stratified old saline groundwaters with high enough densities at the disposal depths to ensure isolation from the near surface environment. Now, other geological and hydrological criteria would of course help, but none of them are showstoppers. And most geologists have long believed that these sort of conditions do exist at depths of a few kilometers over much of the continental basement, especially the old cratonic areas. And this is certainly consistent with the evidence from the relatively few boreholes that have actually sampled these depths. And they show that the probability of finding these conditions does increase with depth, and especially the isolation from the near surface waters. On the other hand, geophysical and geochemical evidence indicates that the continental basement is far from uniform, begging the question of just how widespread these key criteria for deep borehole disposal really are throughout the whole of the crust. I think the truth is that while we know the necessary conditions for deep borehole disposal do exist in some areas, we don't yet know enough about the continental crust beyond the top kilometre or so for most places. And so we can't really make a quantitative estimate about how much of it could be technically suitable. From the socio-political standpoint, I'm not really qualified to comment, but in his recent book on nuclear waste politics, Matthew Cotton advocated deep borehole disposal as the most likely way of achieving public acceptability for siting disposal facilities. So overall, I believe that even if the proportion of the continental crust technically suitable for deep boreholes turns out to be less than we anticipate, the siting options are very unlikely to be less than for mined repositories, which after all have not proved exactly easy to site.
Yeah, very true indeed. Chris, I think you had some thoughts on this as well. And I mean, you were looking at, originally, I think deep isolation was looking principally at sediments, but now you're sort of broadening out a bit. Do you have some thoughts on siting and siting possibilities?
Yeah, I'm very similar to Fergus's point. I think, you know, we're not yet at the point where we've got a sort of quantified assessment of, you know, how much the world is suitable, but our view is that you know, depth itself, you know, just opens up more potentially addressable host rock formations than are feasible when you're thinking solely about a mined repository. So we see this as opening up more opportunities, more localities in which appropriate rock formations can be accessed. So yeah, we think that, and the second point we'd echo. I mean, this is an issue which is, you know, probably less researched than issues around mined repository siting, but I think there is some evidence to suggest that there is a potentially, you know, an easier. There are elements of this solution which are potentially more acceptable from a community perspective. So I know that's something that we're keen to explore further with waste management organisations. But I think those two things of potentially more locations and potentially more acceptable locations are important factors in Borehole's favour.
So you're getting some sort of feedback from communities that deeper is more acceptable than convention.
Yeah, we are. So the combination of the depth and, as I mentioned in my presentation, the potential for more modular, more shared disposal across multiple communities. Those two things, I think, are potentially important factors around consent.
Yeah, I mean, one of the questions that arises with deep borehole disposal is how much effort needs to be put into characterising the rock volume you're going to dispose into. And of course, we know that deep geological repository programs put a lot of resources into doing that. And there's the argument that the deeper you go, the more difficult it is to do it, and a counter argument that says maybe you don't need to do quite so much. I don't know, Dirk, do you have any thoughts on this, or on what kind of siting environments perhaps more of interest?
Well, if you don't mind, I might throw in some data about Australia on the previous question around the borehole disposing, opening up a much wider range of siting options. You know, as you go deeper, assuming there is no technological hurdle to drill large diameter holes, you will have more options. theoretically, because anywhere you go, you will eventually hit the crystalline basement rock. So as an example for Australia, about 50% of the continent, and it's a big place here, it's about 8.6 million square kilometers, has a basement rock at less than 250 meters depth. So the top few hundred meters will probably be fractured, so you may need to go to 1,000 meters or so to find tight rock that give you appropriate containment. From which point onwards, you have lots of degrees of freedom. So I think the take-home message is that this disposal concept, which has a very small footprint, that allows you to go sufficiently deep, flexible in terms of geology, not just crystalline rock, but also mudstone, claystone, and even salt rock. I think the siting, or the range of siting options indeed, are much wider than for a GDF.
Right. Okay, I mean, at this point, I'd actually like to bring you in, Philippe. I mean, one of the things that came up yesterday was, and is very evident from the presentations we've had today, is what kind of national programme might deep borehole disposal be of most interest to. And we've heard that certainly if you've got a small inventory, it could be something central to your case. But for some of the countries with very large and mixed inventories, then we're also beginning to hear potential there. What's your thinking on this?
Well, yeah, as you mentioned, Neil, indeed, I think it's obvious that small countries with a small inventory take an interest in this because of the cost of constructing a borehole is less than a mine repository. Now, if you go to larger inventories, obviously that cost balance shifts in the favor of constructing a mine repository for all the waste. But you addressed it, I think, yesterday already very well in your presentation, that there's some scenarios or some cases where a subset of the large inventory could be envisaged for borehole disposal. For example, if you have a waste stream that does not meet your waste acceptance criteria for your disposal facility, or if you have a subset of your waste that you want to dispose of very soon in the very near future, while your GDF will only be built decades from now. So these might be scenarios where a country with a large inventory may take an interest in borehole disposal. Chris already touched on the fact that it has a modular character, which could open the possibility to geographically spread your disposal sites. Now, I do not know to what extent this is a theoretical consideration. First of all, of course, if you're gonna geographically spread your boreholes, you will need to do also much more site characterization work. You will need to develop a specific safety case for each of these sites. So there your effort increases. And also we see that until now, the tendency in large countries working on geological disposal is that there's a tendency towards a centralized facility. Is this because there's a lack of a modular solution like borehole disposal, or if it's because there's a strategic preference to go for a centralized facility? That we cannot say, but I'm a little bit more skeptical about the idea to geographically start spreading your boreholes. But to answer your question in short, small inventory countries, I think it's logical that they take an interest in this solution. And for the countries with a large inventory, specific conditions may let them take an interest for a specific subset of their inventory to look into borehole disposal.
Yeah. If anybody else on the panel has any thoughts on this or anything, please do jump in.
Neil, yes, okay. I would just add a small comment to that, and that is that when, or if and when, the diameter and depth of the achievable boreholes increase and the cost decreases, as is almost inevitable with experience and practice, then these considerations for, the inventories might well change. They may favor even more applications.
Mm-hmm. Okay. I'd like to bring up another question which crops up from time to time, and that is to do with retrieval of waste from deep boreholes. When I first looked at this concept many, many years ago, one of the attractions was that you were going so deep that there was no possibility of retrieval, and certainly when you're looking at disposal of fissile materials, then you're going into an environment where you could make the system practically irrecoverable from safeguards purposes. But now, of course, many national programs are interested in having retrievability, and indeed some of them have it in law, that retrieval of waste for a particular period after disposal is important. What do you think as a panel that deep boreholes have to offer? What are the pros and cons of this? Any thoughts?
Well, I'll make a comment if you like. I don't really believe there's a conflict between these nowadays. I mean, retrievability is not the issue it was even 10 years ago. When it was taken to mean retrieval forever, it was evident that deep boreholes would find it far too difficult and expensive to recover any waste. But nowadays, in many countries, admittedly with some notable exceptions, I think realism prevails, and retrievability is being accepted as meaning recovery up to the point the repository is closed and sealed. Now, beyond this point, retrieval of waste packages from a mined repository is likely to be just as difficult and dangerous as trying to retrieve it from a deep borehole, perhaps even more so. So I don't think the issue of retrievability is the showstopper it was 20, 30 years ago.
Oh, interesting. Jeff, you were going to say something on this.
Yeah, although it's a little bit along the same lines as Fergus, that the retrievability regulations as written tend to deal with the operational period, and they're aimed at a mine repository where the operational period is tens of years to 100 years, and they want to make sure there's nothing's gone wrong. For borehole disposal, the operational period might be a year or two, at which time it's sealed up, like Fergus said. And of course, the main objective of waste disposal is isolation. So once you've finished emplacing, we don't want to, have some, I'll call it artificial, but it's a little bit socio-political, constraints in place that make it less isolated just for the purposes of disposal. Secondly, in the US, the regulations for retrievability are a little, I know what's the right word. There's different ways you can achieve them. And achieving the retrievability objectives, it doesn't say anything about how difficult or how costly it would need to be. So you could come up with scenarios to, quote, retrieve waste from a deep borehole, solution mining or something like that, which of course makes no sense from a financial standpoint, but would achieve the regulations. So,
yeah. Pat.
Yeah, I would toss in that there's a multi-billion-dollar industry called oil field fishing. That this is what they do all the time. And we've talked to retrieving stuff. They don't pull out waste packages, but we've asked them and said, could you do it? Could you go back in? And their response is always, oh yeah, we can do it. We do that sort of thing all the time. So I agree with Fergus and Jeff that it's not the obstacle that people claim. There are ways to do it. You can overcore, you can use classical fishing, or you could do the solution mining. But I would highlight something that Fergus pointed out, which is that there's this general presumption that retrievability from a mine geologic repository is cheap and easy. It's not.
Yeah, very true. Yeah. Jeff, back again, please.
Yeah, just a quick example. So, we have the awesome mine in Germany where they're, planning to retrieve waste that hasn't even been sealed, and we'll see how successful that operation ultimately is.
Yes, exactly. Okay, I mean, I asked yesterday, my last question on my list was, where did you think we're going to be in 10 years' time with deep borehole disposal? Things have moved on quite significantly, I think, in the last decade, which is very encouraging. We're learning more as we move along. Where do you think we're going to get to, and what is it going to take to move us forward? Pat, was sort of asked this question yesterday when we asked him what it would need to bring it up to the same level in the regular cycle of regulatory approval and so on. And he said we needed a field test. So is that your sort of considered opinion as a group, that we're not going to be able to get much further forward now because we've developed the concept and now we actually need to do some more field tests? Is that really the next big hurdle?
Neil, could I make a suggestion? Could you poll the panel on that question? I'd like to, I think we'd like to hear from everybody on, that's a particularly important question. And I wondered if you just go around.
Yeah, sure. I mean, one by one, make it brief, but one by one. Is it a field test now is absolutely essential? Are we going to be held up if we don't get a field test? I'll begin with you, Fergus.
Yeah, I agree with Pat and everybody else that the full-scale engineering demonstration has to be the top priority, as it's required not only to show the technical viability, but also to stimulate the investment in R&D needed, which we need to gain the required level of regulatory approval. But it's also necessary because it could demonstrate that the technology exists or soon will exist to identify suitable sites. And this is a very important point. If we can't identify the sites, we're stuck. But that just involves drilling small exploratory boreholes, which can properly characterize the immediate and the surrounding geology, the structure and the hydrogeology. And for the critically important hydrogeochemistry criteria, this is likely to require the development of special downhole fluid sampling techniques as a kind of matter of urgency. That's an area which we have a slight problem in. You cannot easily sample the ambient fluids down a borehole without risking contamination by the drilling fluid. And that's an issue I think we need to address.
Okay, take that as being a very strong yes. Carl, yes. How about you?
Yes, completely agree. And also we badly need a characterization borehole. Wearing my modeling hat, the models are only as good as the input variables, and we need to improve those input variables, and we can't get those without a characterization borehole and improve data.
Exactly. Dirk, I guess there's almost no point in asking you because you're planning one anyway, so, but you might want to.
Yes, indeed, and there's multiple elements to the demonstration test, as we've heard several times. There's demonstrating the emplacement technology, the drilling technology, the sealing, being able to monitor that the seals perform properly over a sufficiently long time, and then of course the safety assessments, and then finally a final safety case, such that also the regulators are confident that this is a suitable disposal option. So absolutely, we need the test, and we are confident that if we get the funding, we will be able to compile all those elements in let's say about 7 years, and then hopefully other countries will follow suit.
Yeah, Jeff.
So I guess I'm in violent agreement with everybody else. I think there's two key aspects to a field test. You know, for a deep vertical hole, you know, the first is, as Fergus said, is making sure we can collect enough geoscientific evidence at depth to show that we truly have the characteristics we need for long-term isolation. But the more important is the demonstration of the shielded surface handling and emplacement technologies. That's something that hasn't been done, you know, at a proper scale. You know, again, it's what Dirk had laid out in his presentation, and I think that's the number one key thing.
Indeed, yeah. Vladimir.
Thank you. I would highlight the importance of involvement in the process of different types of stakeholders and in rather early stages. First, in the stage at the stage of conceptual discussion of the borehole disposal, and as early as possible to involve in this discussion regulator body and other potential stakeholders in order to prepare them to discussion of specific concrete project when siting is started. And I think that when the discussion is based on any referable point, it would be easier to get understanding and confidence within stakeholders, and such point of reference, I would identify safety case for a deep geological repository, because it is more or less familiar to all potential stakeholders now. And when the discussion is based on these general key elements of safety case, and then specificities of deep borehole disposal explained and safety is demonstrated, I think this could facilitate the process of demonstration of the safety and then promotion of the project itself. Thank you.
Yeah. Thank you. Yeah, another yes. Thank you very much. Chris, there's no point asking you. You've already done one, I guess, but I guess you might like another.
So yeah, I mean, we agree that a large-scale demonstration is needed. I'm on board with everything everyone said. The one thing I'd add though is I wouldn't want listeners to the webinar to go away thinking that this is just a sort of blue skies idea that now needs demonstrating. The individual components of much of this are proven, they're mature, they're in use in different industries. Many of them have been, you know, we've done demonstrated retrieval in this, and many of the organizations around the panel have demonstrated and tested elements of this. What we're missing is that integration demonstration, which shows how it all comes together and builds trust and confidence in the community. That's the key thing I think we need to sort of make the next step forward. But there's been lots of testing and demonstration and already in a less integrated way.
Yeah, absolutely. Couldn't agree more. Philippe.
Yeah, I share the consensus here. I just would like to draw the parallel with the borehole disposal of disused radioactive sources. So that idea to do that was initiated in the 1990s. It was an idea that countries with a small inventories of disused radioactive sources can find a feasible and affordable solution in borehole disposal. It took then about 10, 15 years to further work on the design. But now that we see that Malaysia is actually working on implementing that concept, we see that it triggers a much wider interest, and countries that are in a similar situation as Malaysia start to also mention that they're thinking of following that route. So it seems that as soon as one is really taking it the step further, whether by a demonstrator or a real project, it really starts to kick off a wider interest. So I agree that I think if there can be a demonstrator, it could help to move it to the next level.
Right. And Havard.
Thank you. I'd hate to be opposed to the consensus by this point, but from the perspective of a small inventory nation, I find the idea of doing this twice in each country, prohibitive from a cost perspective. So I think it would be important that, for instance, the Australian demonstrator could be used to demonstrate the necessary, make the necessary demonstrations for us, for instance, or at least that everyone involved could agree that a certain level of confidence could be derived from existing demonstrators, so that you wouldn't necessarily make a duplicate in each nation. I think at least this is a question to keep in mind.
Yeah, I think when we're thinking of field testing here, we're certainly thinking of one or 2 field tests that could be widely applicable. And the technologies that were demonstrated there could apply anywhere. So it wouldn't be every country having to do its own test, I agree. Finally, Pat, well, you already started this off, so I'm assuming you're going to say yes.
Yes, and I would echo Chris's point. The science, a lot of that, the science has been done. What we're aiming for is a shift in public perceptions. Sure, there are hundreds of thousands of oil and gas boreholes out there, but all people see is a drill rig for a few months. A demonstration that we know what we're doing, that the project is integrated, and we know it from cradle to grave. It's a public perception challenge, which I think could only be achieved by a demo project.
That's great. Well, there you go, Bob. I think more or less uniform response there that something like this is definitely needed.
Well done, Neil.
Given the time, it's probably a good time to start wrapping up the panel session. We've rather overshot our time again today. If I was able to try and bring together everything that's been said over the last 2 days, I suppose very briefly what I'd say is I'm impressed now that the concept is really becoming mature. Certainly over the last 10 years, things are beginning to come to a focus, whereas before it was just a group of disparate ideas and concepts. There's a lot of common thinking now, a lot of more maturity than there was even a few years ago. And I think we're also beginning to see ranges of engineering solutions being put forward to some of the common questions that have been asked about borehole disposal. For example, what happens if you drop a canister and things like that. It's not just that there is no answer, there are several answers now. But all of these things are pointing us towards field testing, as we've just heard in the last round of the table there. That this is really a very useful step to move things forward now. And I think supporting all of this, the other thing that's impressed me, and which wasn't there a few years ago, is that there's a growing number now of safety assessments, which we can begin to form a basis for the overall safety of deep borehole disposal. Until 5 or 6 years ago, there were no safety assessments of deep borehole disposal. We've seen 3 in this webinar now. And of course, they're all indicating that it provides an equivalent level of safety to any form of deep geological disposal. I think all of this is important, the fact that we're able to move forward, because what I also heard is that if we were able to deploy deep borehole disposal in a national program, it's going to offer that program some degree of flexibility and some degree potentially of cost savings if it was to be included within the spectrum of solutions that the national program would have for its total waste inventory. So all very promising, I think. And I think it's been great to hear from you all. I'd like to thank you personally as a panel for all of your contributions and talks over the last 2 days. And I hope our audience has gained something from it. A reminder to everybody there, if you've got any questions and answers, you've got a few moments to put them up there. The panel will be providing written answers to groups of questions, and they're all going to be posted on the IFNEC website along with the recording of the proceedings from today. So my thanks again to everybody, and I'll hand you back to Sean to close the meeting.
Thank you, Neil. Well, first, I'd like to thank Neil and also the Secretariat for the fine work they've done in putting together this webinar. Like all really worthwhile events, not only has it provided a great deal of information to the broader community, but it's raised many questions which provide fertile material for further investigation by, I would say, the working group, as well as contributors and attendees to this meeting. So I really look forward to future work being conducted both within IFNEC and outside regarding the use of deep borehole technology to dispose of spent fuel and high-level waste. I would like to thank all of the panelists for your time, your contributions. I really hope that we can follow up after this event and for future collaborations. To everyone who attended today, thank you so much for your time. I hope you will also, as Neil asked, submit questions to the group so that we can continue this dialogue in future. For now, be safe, be well. I look forward to working with you again in the future. Take care.